Hi to everyone, and thank Martin and Acer for the organization. And I also wanted to connect my talk a bit to what Martin said yesterday, in that the definition of agency that I will give will fit with 2 out of the 3 points that Martin brought up. So on the one hand, the system has to be an entity, one thing, to be an agent, and it has to be separate from the environment. And in the first part of my talk, I want to show you a way in which the integrated information theory actually could provide a means to divide a larger dynamical system into agents and the environment. And the second part of the definition of agency will hit something that also Susanne brought up, which is an agent has to act upon its environment in some ways. What is missing is a notion of goal-directedness. And that doesn't mean that that might not be necessary, but I want to give you a very minimal starting point for what is required. And I also want to say that all my work is done in discrete dynamical systems, just as what Martin introduced yesterday. So, and the diagrams you will see are basically diagrams of interacting nodes, so like neural diagrams. So it's not state transition diagrams, but mechanisms such as logic gates that interact in certain ways. And that's all the preface I want to give, and I hope you can enjoy the video, and given that it's pre-recorded, I hope it's going to go smoothly, and then I'll be available after the talk for questions. Thank you.
Thank you.
So, okay, so we will play the video now. So can you see, the video?
Yeah, on the screen, yeah.
Okay.
Hello, everybody. My name is Larissa Albantakis. I work as a scientist at the Wisconsin Institute for Sleep and Consciousness, together with Giulio Tonoli, on the integrated information theory of consciousness. But today I want to tell you about my work on agency and autonomy within the causal framework of IIT. A question that has been interesting me for quite a while is simply, what is an agent? And first I give you a minimal requirement, which is that agents are open systems that dynamically and informationally interact with the environment. So this is not a definition, it's really an obvious minimal requirement. Anything that doesn't fulfill this can be an agent, but already the simple requirement poses 2 problems. The first problem is, how do we distinguish an agent from its environment? So in biology, for example, organisms are typically taken for granted. When we have a system, we know what the organisms are within that system. However, if we're just giving a larger dynamical system that consists of the environment and the agent, there aren't good tools to figure out which part of the system, which subset is agent and which subset is the environment. The second question is related to the problem that agents are supposed to act upon their environment and to act autonomously, so to act from within themselves and not driven by the environment. And so the second question is, how do we distinguish autonomous actions from mere reflexes? And here we can distinguish 2 scenarios. One is that we already know that we have an autonomous being like Leonardo here on the left, and we have a automatic system, a robot or a machine, and they both are able to perform the same action, here pressing the green button. And mechanistically, there is, let's say, atoms that are activated, and in the end, there's a button pressed, right? So how do we distinguish an action caused by an autonomous system from an action caused by an automatic system? And the second possibility is that we have two, like in both cases, we know that it's an autonomous system, or it's the same autonomous system. The same system, here Leonardo again, can perform an action because they choose to or they want to, because of intrinsic causes, or perform the same action as a reflex. So here, if we, for example, give a TMS pulse to Leonardo's motor cortex, he may push the green button even though he didn't intend to do so. So if we ask here, what was the cause for clicking right? An answer that a neuroscientist could give is that neurons were activated and interacted with other neurons, which then triggered a motor response. So if we are at that level of interacting neurons, how can we mechanistically distinguish the action that was performed voluntarily from the action that was performed as a reflex? And here I will give you a first minimal working definition of what an autonomous agent is and what I think is required for an autonomous agent. It's a twofold definition, with the first point being that an autonomous agent must be an open system with stable, self-defined, and self-maintained causal borders. And it also has to have the capacity to perform actions that are at least partially caused from within. So the big question is, can we quantify this? And there has been some related work a lot in the past 20 years, let's say, and a lot of it is within the realm of information theory. So I want to highlight the causal part of my definition, which has some implications on the measures and the quantities that I will define in the following. So the question is, can we quantify this? Again, the agency, whether a system is an autonomous agent. And unfortunately, for anything remotely as complex as the human brain, the answer there is definitely no. But we can look at very simple systems that are only comprised of a couple of interacting elements, such as these animats, which are simulated adaptive systems. They have sensors that can receive inputs from the environment. They have hidden neurons and motor neurons that allow them to move within the environment. And their movement and their actions are determined by, in this case, a deterministic Markov brain. So the function, as well as the connectivity between the elements, is encoded in a genome that can evolve. And so a possible task that these animats perform is, for example, in most of the slides that follow, it will be the agent has to catch or avoid blocks of certain sizes. So for example, catch small blocks and avoid large blocks. And we start the animals out, we start their Markov brains out without any connections between elements. And then through a lot of cycles and generations of selection and mutation, based on fitness, they will evolve a more complex network structure here, and also that comes with then the capacity to actually perform this task reasonably well. So yes, so the question is, can we view this at all as an autonomous system, or is that a too simple starting point? Because it's so small and not complex at all, we know all the parameters. So this is a good question, and the nice thing about these agents or animats is not that you have to view them as an autonomous potentially autonomous system that is able of performing actions caused from within, but if you think they do not count, then at least they force you to give precise reasons for why they don't count, so what they are lacking. If you do think that they could be autonomous, then this is measurable, or you can point to specific properties they have. And so I would argue that in the least, these animats rely on internal states and memory, and they also demonstrate context-dependent behavior. So as you can see here, there's a block falling, and the agent might go in the one direction for a while and then keep following it. So it's not always performing the same action, giving a certain sensory input, but it also relies on its internal state. And in that sense, there is at least some amount of detachment from the environment. So with the definition I gave you, I want to show you that the causal framework of IIT can actually help to quantify the two parts of the definition. So the first part is that we want a system with stable, self-defined, and self-maintained causal borders. And so the question is, how can we identify whether a system has self-defined causal borders? And I want to show you how that can be measured using integrated information on two examples. One is evolved artificial agents, the animats I already introduced. And the second example is a biological example of the fish and yeast cell cycle model that we did together with Sarah Walker and one of her postdocs. So the question here, given an agent such as the artificial system of an animat, is to be or not to be. So is this an entity? And you might say, well, of course, it has sensors. I know what it is. It has motors, and I can see that it's separate from the environment. But what if you take the environment also as a set of mechanisms that just interacts with these nodes? So in this larger dynamical system, how can you identify which part of it is the agent? Like, could it be this part or a smaller part? Which subsets in this system of interacting mechanisms might correspond to an autonomous entity? And the goal is to identify these autonomous systems in an intrinsic, which means observer-independent way, of identifying the borders, and I mean the causal borders of a system. And the answer that is given by the integrated information theory is that the important thing is to be integrated, because that determines whether the system can exist as a whole, above or a background of external influences. So what integrated information, or the measure, we call it big phi with the Greek letter, determines is that a system that has integrated information larger than 0 constrains itself to some degree above the background of influences from outside. And such a system that forms a maximum of phi, a subset within a system that forms a maximum of phi, is called a complex. So one implication of this, of the necessity of being integrated, and all the elements of the system being able to constrain the rest of the system in some way, means that recurrent connections are necessary for autonomy. So something like a feed-forward system cannot exist as a whole, cannot be an autonomous system, because there is no way to draw borders in an observer-independent way. as like I can draw borders around the subsets, but within each of the subsets that I select, part of the elements will necessarily be determined exclusively by mechanisms outside of the system and are not constrained at all by the systems, by the mechanisms within the system. So this is an intuition that I want to give you that is independent of the specifics of IIT. So as I said, our goal is to identify the subset within a system that forms a maximum of integrated information, because we can have several subsets, and in this case we can see it, that all specify some degree of integrated information. But our goal is to have a system, so causal borders really means that for a system such as here A, B, and C, if I add an element to the system, I will decrease its integrated information. And if I take away an element from the system, I will also decrease its integrated information. So in that sense, it forms a maximum of integrated information, but it still is able to interact with some outside elements and mechanisms. And how to compute phi is best explained in the paper accompanying the IIT Python toolbox, but I do want to give you a short sense of what is actually measured with the integrated information, what phi captures. So one important thing is that phi is entirely about the causal interactions within the system. So if we look at a subset of a larger system, then all we are interested in is how the elements within the subset constrain each other, and the elements outside of the system, such as here element D, will be fixed as background conditions. So in this case, element D is in state off, and we fix it in that state, and it will be off throughout the causal analysis. So that means that all interactions of A to C are conditioned on the fact that D is 0. And conditioned on that fact, we get the following transition probability matrix here for the elements of A, B, C. And the transition probability matrix states how if the system is set into any of its possible states, what is the next state going to be. And in this case, it's a deterministic system, so there's always going to be one state that the system will enter for sure, but we can also analyze probabilistic systems, and in that case, each row would be a probability distribution of what state the system is likely going to enter at the next time step. And the TPM is the starting point for the entire integrated information analysis. So from here, what we want to do is to unfold the causes and effects of the system in a particular state. So ABC is our candidate system, and it is at its current moment in state A being off and B and C being on, so 0, 1, 1. And because the system is in that state, it necessarily constrains the possible states at t-1 and also the possible states at t+1. So we ask for every element within the system. So for example, A is an AND gate. What does the fact that A is off tell us about the previous state of the system? And what does the fact that A is off tell us about the next state of the system? We ask that for all individual elements, but also for pairs of elements and actually every subset within the system. And this is an important point because it's a very different approach than is usually taken on causal interactions. So IIT takes a compositional approach to causation. So typically, causation is either analyzed from a reductionist perspective, which means that I apply perturbations to the inputs of the elementary mechanism. So I set the system into state 0, 1, 1, let's say, and I look what happens at each individual element. So A, B, or C. And those we call the first order causal distinctions within the system. Another way that is common, especially in physics, is to look at the dynamics of the system as a whole, and that's called the holistic perspective. So I can set the system into a state, and I can observe which state it is going to enter next. And if I do that for all possible states of the system, then I have a perfect description of the dynamics of the systems. And so with both of these single order descriptions, I can perfectly predict what is going to happen next. But what the aim of IIT is to capture all the information that the system has about itself in its current state. And that is really given by all the subsets and all the information that each subset specifies in an irreducible manner about the prior or next state of the system. So we count, we check all orders of subsets. So first order elementary mechanism, combination of two elements within the system, and so on up to the highest level, highest order, which means what does the system as a whole say about itself. And we count all of these subsets that specify irreducible information, which means more information together than any partition of the elements could by themselves as possible as mechanisms within the system. So if we do this for our system ABC, we find 6 intrinsic mechanisms. The only mechanism that is missing here is AC. So A and C together in this particular state do not specify information above and beyond A and C separately. So all of the other subsets within the system can specify something about their causes within the system and something about the effects within their system. So we can take these causes and effects and put them into what's called a cause-effect, into a cause-effect structure. And just as a side note in terms of consciousness, so if IIT is taken as IIT is a theory of consciousness, and what it states is that the quantity phi would correspond to the level of consciousness within of a system, and the cause-effect structure would determine the experience that the system has in its particular state. But that's just a side note, and here we focus on the quantitative framework to identify causal orders. So once we have this cause-effect structure, so all the internal mechanisms within the system, there's still one problem, because also a system such as this, the XW by Z system, will specify intrinsic mechanisms and so on, but clearly this is not one autonomous system, but everybody can see, I think, that these should count as two separate systems because none of their elements actually interact at all. And so what we test once we have identified the cause-effect structure is whether the cause-effect structure of the system is integrated. And for that, we partition the system in all possible ways. And a system has some degree of integrated information if all partitions mean that some mechanisms, some of the information specified by the intrinsic mechanisms will be lost due to the partition. So we find the partition that makes the least difference, which in this case is cutting or noising the connections between from A, B to C. So we render those errors ineffective, and by doing so, we destroy a large part of the information that A, B, and C specify about each other. And integrated information phi, the quantity, then measures the difference between the intact cause effect structure and the cause effect structure after the partition. All right, so with that, as I said, we do this for all the subsets within the larger system, and we can identify the system that has self-defined borders as the one that has a maximum of integrated information, which here happens to be ABC. Now, whether these causal borders are state dependent. So it could be that if the system were in a different state, the subset with highest phi could be a different one. And I will say some more about this once we look at the biological example. But really, the question whether there are stable borders means that we have to evaluate the subset over all relevant time steps and see if the borders that we identify will be stable or not, and that will depend on the properties of the system. Okay, so we have applied this measure already a little while ago to these evolving agents, and we tested agents that evolved in two different tasks, or multiple tasks actually. So here I show you one that is the very simple task, which is catch blocks of size 1, avoid blocks of size 3 in this block following task. And we compare those two agents evolved in a more difficult task where two sizes have to be caught, 3 and 6, and two sizes have to be avoided, 4 and 5. So this task is more difficult because it requires more memory, as the animats only have 2 sensors, and so they have to count how long the blocks actually are. And we find that for the more difficult task, the integrated complexes, so the subsets of the system with maximum integrated information become larger on average, and the phi value of those systems will also be larger than for the simple task. And this is especially noticeable here with the red line. The red line is the subset of agents that actually reached high fitness in the difficult task. And so it reached the same fitness level as the set of agents evolved to the simple task. In that case, the difference is even larger. All right, so another interesting fact about the study was that restricting the animate sensory and motor capacity actually led to higher integration. And that makes sense because even though the task itself doesn't change, it changes from the perspective of the agent. So now with just one sensor, the simple task also requires more memory as it has to be solved with not through sensor input, but through the internal mechanisms of the agent. And that leads, again, to higher integrated information, larger complexes. So, and another system that shows to how that intuition fits with, here, for example, we have a camera, and the camera has a ton of sensors, right? And it can have a quite complex input-output function, so the camera can show you all pictures you take with it, right? But the behavior of the camera is entirely driven by the environment, and at least in these old cameras, there's not much interaction between the pixels, and so the phi value would definitely be 0. And here it seems clear that this camera is not very, very smart, or the fact that it can just copy the inputs doesn't necessarily seem so complex, but there are often cases where it's not clear if the complex output or the complex seeming output of a system requires complex internal mechanisms or not. Okay, another point I want to make is that this, for these agents, the simple task, we can find perfect solutions of these tasks with both integrated systems and not integrated systems. So here you can see two solutions. One is this, that is entirely feed-forward with just sub-loops of these elements, so it's basically modular, and another one that has an integrated core where the elements constrain each other. And what that means is that, so this corresponds to the initial example that I gave you, where we can have two systems, one being a potentially autonomous entity, and another that's just like a machine going through the motion, performing at the same level of fitness or intelligence, if you want. And we can also compare that to these artificial neural networks that become smarter and smarter and can do really great things now, like play Go and win against humans doing so. But so according to IIT and the integration requirement, such a system could never form an autonomous entity and would for that reason not count as an agent. So implementation matters for agency and autonomy and not just function. Okay, here's the biological example that I promised you earlier, which is the yeast cell cycle model. And we analyzed this. It's a very small system that is a Boolean model of the cell cycle, which means that it's made of binary elements that correspond to proteins that get activated or deactivated throughout the cell cycle. And if it's initialized in the correct state, the states that the model will go through correspond to the biological sequence of proteins that is observed. And for this system, we found that for every state within this biological sequence, the whole system, except for an input node that activates the cell cycle, basically forms a maximum of integrated information and has causal borders where the elements within it constrain each other above the background, which in this case is this input node. And most interestingly, I guess, is that this is not true for a functionally identical network. So this network is functionally identical in the sense that if you initialize it at the same correct state, it will also move through the biological sequence of states, yet it lacks some of the constraints of the system that are thought to be important for robustness against external perturbations. And that system does not form a complex in every state, and its borders are not stable across the sequence of the cell cycle states. Okay, so with that, I come to the second part of my agency definition, and I want to talk about the capacity to perform actions that are partially caused from within. So how do we identify the causes of an action first place? And again, I want to show you how we can do that within the framework of IIT based on the example of the animats, and then also talk a bit about a new project that we just started on applying this to classifiers. So here we have the same system again, but now instead of one node that is interacting with the system, we have an input and an output. And the situation is a bit different because, here what we observe, we take the role of the observer of the system, and we know everything about the system, and we know that it transition from the state 0, 0, 1, 1 to the state 1, 1, 1, 0. So at t, the system output a 0. And even though we know all of this, there's still a question that remains, and that is, so what was the cause? What was the actual cause for the output to be 0? And in this case, the answer is relatively easy to find, because the output is an AND gate. It received input from these 3 nodes. So it would be on only if all 3 of them were on, but A is off, so A in this case is the reason for the output to be 0. And I hope you could follow that logic. Another way to see it is that if we change the state of A, the output will change, but if we change the state of B and C, the output will not change. And in general, it's a bit more complicated to find out what the actual cause was of an event. And what we have to do in that case is again search over all possible elements, and we find the set of elements that most reliably basically predicts the state of the output, compared to rendering the connections ineffective. And with that formalism of actual causation, we can now quantify whether the actions of an agent are caused from within the system or are due to sensory inputs. So this A is the cause, as I said, and this is displayed here. So something like a reflex brought to the level of the animats would be that there is a sensor input that directly determines the action of going right. In this case, we would find that the actual cause is outside of the complex which forms the autonomous entity. In this case, the movement, even though it is performed by the animate, is not an autonomous action. And an autonomous action, even in this deterministic system, would correspond to an actual cause within the integrated complex. And again, so we can actually quantify this if we run an experiment where so we have an animate that performs in the environment, is catching blocks, and here you can see the time series of states of this agent, and we can pick a time state, and in this case the motors are in state 0 and 1, and we can identify which elements, the sensors or the hidden elements, were the actual causes for individual motor states or the motor states together. And we can later in the sequence, so the agent performs the same action, but in this case we might find a different set of causes for the same action. Another thing we can do is, so the actual causes first give the direct cause, the proximal cause for the action, but we can use the same framework to trace back the causes of the causes for an action over time. And so the way to do it is that we identify the actual cause of the motor action and then the causes of the causes and all the way back as far as we want to. And doing that, we can then quantify how long and how many internals were involved before the entire state, or before all causes basically come from outside of the agent. And we did this quantification for 3 different tasks in this small conference paper that we had just last year. And So it's the baseline task is again the simple task that I've explained before, where blocks of size 1 have to be caught and blocks of size 3 have to be avoided. Then there's a harder task with 2 sizes, and the 1 sensor task, which is the baseline task, but more difficult because the agent only has 1 sensor. And importantly, across these 3 different tasks, we did not find any significant differences in the motor connectivity across conditions. So if you just look at the connectome and you ask is there a difference of how the sensors and the hidden nodes are connected to the motors, you don't really see a difference. But with this actual causation and backtracking analysis, we do find a difference between the conditions, and maybe not so surprisingly, in the condition with only 1 sensor, the hidden elements play a larger role in determining the motor output than the other 2 tasks. And if we measure the time that the causes of the causes reverberate within the agent, as opposed to going to the sensors, then we find that there's more memory and involvement of the hidden states in both the 1 sensor and the hard task. So that kind of corresponds to a more distributed computation with more memory in those tasks. And we can apply this to classifiers now, and you can see an example on our website with the link here. And so we can we can record, so we train a network, we have a trained network. In this case, it's trained on images of, or not images, but properties of different irises, and it will classify which iris, which flower did the input correspond to. And so we can take the input layer, which here is a binarized number, and we can take the output layer and ask which input nodes were most relevant for the given output. We can do so across layers. We can also backtrack the causes of the output to identify the most relevant neurons across layers. And the reason to do this for us is mostly to kind of make sure that what we measure and what we identify with the actual causation framework does make sense. And those classifiers are nice because there's a lot of other measures that try to do similar things, like identifying important input features. And so we can compare our approach to those approaches. But it's also a causal approach, and that hasn't really been done before. So we also hope to find some insights about how these systems work and how they might be different from more brain-like neural networks. One problem is that, similar to other information-theoretic measures, the analysis is extremely costly, so we can only do small systems for now. And the generalizability of the features that we find are relevant is not necessarily guaranteed to generalize across instances. So we could have another picture of the same flower, and in one case the yellow stripes here were very relevant, and in the other case they were not. But so this is not a problem of the measure, this might be a problem of the classifier and indicative of the fact that it actually works in a different way than our neurons do. So to sum up, there is 2 types of dissociations that I've been talking about as a consequence of IIT. One is the dissociation between systems that are built differently, but they might perform equally well. So you can have an autonomous system and a non-autonomous system that both behave equally intelligently. And then there's the dissociation within an autonomous system. There can be reflex actions and autonomous actions, and I've tried to sketch out how the difference is being approached from the point of view of the causal framework of IIT. So just a last provocative slide, which what I want to emphasize is that functional equivalence in IIT does not imply causal equivalence, and that is true for systems with the same input-output behavior. So here, an integrated system and a feed-forward system that are functionally equivalent for a number of outputs. One forms an entity, the other doesn't. It's also true for computer simulations of integrated systems. So the computer simulation as a whole might not be integrated at all. There might be some subsets within the computer that count, but it is the causal structure, and that is different between the computer and the system that is being simulated. And it's also true even for systems with equivalent global dynamics, and that is something we discussed in our latest paper. And just to very briefly make the point here, so you can have a larger dynamical system where part of it is an agent, let's say, and part of it is the environment, and you have some dynamics here. The system cycles through all its possible states, and so does the subset. And if we just remap the sequence of states here, so we keep the dynamical transition diagram equivalent, just the order of the state change. So from a holistic perspective, the system is still doing the same thing. Then we might still have destroyed the causal borders within the system, and what was an agent before now might not exist anymore. And I hope if you find that interesting, you can look up both our paper and also the paper that we give a reply to some degree, which is Sarah Walker's paper on integrated information, isomorphic feed-forward zombies. And with that, I want to end, and I thank you very much. And I thank our group and also the funding agencies you can see here. And now I hope that the technology works and I can take your question. And thank you again.
Thank you. Maybe Larissa? Okay. Yeah. Okay, there. Okay. So we have a question.
Hello, thank you for the interesting talk. At the very beginning, you spoke about how the system is like self-defining and self-maintaining, or maintaining. And I was wondering, so the self-maintenance, how does the integrated information theory relate to that?
Yeah, so the self-maintenance is really not something that comes as a consequence of IIT, because IIT is a state-dependent measure. So you can apply it at every state of the system, and you will find, potentially find the agents to be somewhere else, or not agents, but the causal complexes, really. But it there is systems that have specific properties, and they will be more prone to having a stable border across time. So it's really a property of the system itself whether the borders that we can identify are stable over time or whether they're not. And in that biological example of the cell cycle, it is actually the case that those borders are stable. And part of, so in general, systems that have some positive and negative feedback, so that have inhibitory and excitatory connections within their elements, they are typically quite stable. Whereas systems that just have excitatory connections or are more easily jump around in terms of where the causal borders are identified.
Yeah, okay. There's another question. Just a second.
Hi, thank you for a very interesting talk. I have a sort of methodological question that I just want to make sure that I understand it correctly. So in all your analysis, you kind of require the God's eye view, meaning that somebody outside the agent is giving you all that information that you can you draw the graphs and things like that. Is that correct?
Yes, basically. So in order to do the analysis correctly, we assume perfect knowledge about the system, right? So if because we don't.
Go on. Yeah, finish your sentence. Yeah.
One reason is that we first want to get the measure right before we go into issues of what do you do if you don't actually have the information that the system if you don't know what you need to know to compute phi for that system. So it's not about identifying causal errors or something. We assume that the causal model was determined by experiment or in the simulation, and that it's given and that it is basically equivalent to the physical system.
Okay, so my follow-up question then is that, like, have you thought about, like, in a way, I mean, we are also agents embedded in the environment. So an agent embedded in the environment can also make observations, but then they are, how would I say, like, they are from within the system, So it's a little bit like how to get objectivity out of subjectivity, because we all only have subjective observations, but then we somehow figure out some mechanisms by which we could say, okay, that is more objective or that is objective than others. So I just was wondering, have you given it some thought? Or?
Yeah, so I think one important point here is that there's a distinction between what we have to do to understand what the system might know about itself and about the environment, and exactly what you're asking for. So what can the system extract from the environment? So the system does not have to compute integrated information. We have to compute the integrated information to find out what the system is. The system just is what it is. And because it is that particular system with the network structure and causal interactions and mechanisms in that particular state that it's in, it has all these causal distinctions. It's not something that the system has to compute.
Yeah, thank you.
There's another one.
Hi, so I had a question regarding your point that functional equivalence is not the same as commercial equivalence, and I think that was greatly portrayed by the distinction between the two different types of networks that you talked about. But what jumps out to me is when you're making the distinction, there's a difference between the need for recurrency and having a feed-forward structure. So when you talk about feed-forward networks, which may be functionally equivalent to a recurrent network, it appears to me there is a need to talk about a degree of agency. So, for example, I could have a feed-forward network with some level of recurrency inside it, but not completely recurrent, like you had in your last slide. In that case, would it still not be an agent? And then do we need to talk about the degree of that agency? I'm able to explain myself.
So the system that in order to form an entity, or let's say within a larger system, only subsets that actually are strongly connected, so that have some path that will bring them back, so that the nodes are connected, can form an agent according to my definition. And the reason is that if I have a subset and any part of that subset is connected in a feed-forward manner with another part of the subset, then phi is necessarily 0 because there's only a feed-forward connection. And in terms of autonomy, it means that whenever you have that, there's one part of the system that doesn't know anything about the rest. So there's one part of the system that basically just dumps information, but it never learns about what happened with it, right? So it's never affected by what it does to the rest of the system. And the other part cannot affect the rest of the system. So in that sense, feed-forward systems of any kind are just excluded. On the other hand, of course, the measure gives quantifies a degree of agency, so you can have a more or less integrated system. But being recurrent is really a basic necessary requirement for having phi larger than 0. And I think there was another part to your question, but now I don't remember anymore.
That's fine. Thank you.
Okay.
Kind of in the same line. So let's say you have one agent and it has phi equal to 2, and another agent has phi equal to 4. Can you say something about one having double integrated information data? Or can you make sense of the numbers that you get?
Well, so it basically measures the degree of autonomy from the environment, right? Or the degree to which the system causally constrains itself. So I can have an agent that that constrains itself very strongly. So it means that its own internal state will determine its next state, and not just its next state, but it also has information about what happens to all of its subsets and so on. So it's just the amount of information the system has about itself and the strength with which the mechanisms within the system constrain each other can be more or less.
I guess I might be missing something really obvious, so I'm going to ask your help. Is IIT actually capturing agency, or is it just capturing, so let me put it this way, without considering the technical, let's say, limitations that we might have, would it be not the case that, I don't know, in some chemical soup, some portions, like some parts of the soup might have a non-zero phi, but still we wouldn't call that an agent, perhaps. Like, I don't know, it might follow some gradients or whatever, it might have some non-trivial behavior, but we would still not be calling that an agent.
Right, so one thing is the stability, right?
Yeah.
In the, so in order to identify whether something is a stable autonomous entity and didn't just like appear and then disappeared, which basically means that it cannot act as a stable system, you have to compute phi over its time series. So you get multiple phi values for all the time steps. And then you can see whether you have a stable system. And that might not be the case in your chemical soup. On the other hand, if you have something that does give you stable gradients that are interacting, then let's say something like a cellular internal environment. I'm not a biologist, sorry. But so a cell before it forms its borders or something is just that. It's chemical reactions that are acting on top of each other, like acting upon each other and making a cycle that is, however, maintained somehow.
Thank you. Yeah, maybe I also ask a question. So you also mentioned at the end that if you permute basically how you split the system into 4 different variables, and the agent, the IIT, was it actually the IIT, the complex might disappear.
Right.
Was it complex?
Yes.
Is there then another complex, or is actually the
completely no complex anymore.
That
always should be some complex.
No, there doesn't have to be always a complex. So we have, in the paper itself, we actually have two remappings, one that just keeps the global dynamics and one that even tries to keep the local dynamics, so trying to keep the dynamics at two levels. And actually the latter completely disintegrates, meaning that the maxima you will find at individual elements. So in that sense, you lost any larger group of agents, or any larger set of elements that could be an agent. So it's really about, I mean, what happens if you just remap the global states is you completely change all the elements and their functions within the system. And when you do that, then it's not just a problem for IIT, but it's a problem for any kind of measure of autonomy that will be applied to subsets of the system, because what those subsets are has changed. Because, so even if you have a dynamical definition of what an agent or the board agent are, a global remapping doesn't maintain, in general, the dynamics of subsets of the system. And you can, yeah.
You could, of course, find the coordinate system that maximizes or minimizes some measure, and then you know that. I mean, then you say you include this basically in your measure. You can say, well, my measure is finds the optimal split or coordinate system of the system for doing something, and then I guess you would be coordinate free.
It would still be true that, so what is the typical viewpoint is that just remapping the coordinates wouldn't change anything relevant about the system, right? But you still have then, even like if you choose the description that maximizes, the description of coordinates that maximizes your measure, you are saying that it is different from other coordinates that are.
Yeah. I guess it's just a kind of, maybe it's a hack. I don't know. But yeah. Okay.
I did get a text question. You want me to read that?
Next question. How?
Like,
Where? Can we, you can read it. Yeah.
Some attendee or I guess asked. So asked about the unfolding argument against this type of agent. What if it behaves like an agent, but your measure gives it 0? What is right, the behavior of your measure or your measure? So I mean, the whole point of my talk was to make clear that behavior is irrelevant for determining what the agent is, at least from the perspective of IIT. I mean, not so. The system has to do something because my definition of agency has both of these components. So it has the being an entity and acting upon the environment. But in order to be an entity, you don't have to do anything really in particular. Yeah, so I could say a lot more to that unfolding argument issue. But I think for something like agency, whether something is an agent or not is really not testable in a strict empirical sense, because it's always that you define, and there isn't going to be an independent measure that can give you a yes or no answer on whether you're correct, right? I mean, as you said, Martin, in your talk, ideally we want our definitions of agency to fit with the examples that we know and be useful, so that we would identify organisms and the like. But I mean, it's really a proposal, more of a framework, is a testable theory of agency. And with consciousness, that's different. That's the main part. With consciousness, you can actually test, but not with agency.
Okay, I don't know if the guy can say thank you, but maybe you take. Okay, you take the last question. No, he can say thank you. He say thank you. Good.
I think it's a simple question. So we know, based on IIT, we think the feed-forward network has no phi, and but we also know in the IIT paper any input-output correspondence can be implemented by the feed-forward network. Yes, and another thing is in some of your experiments, when the agent, the network try to learn a task, it intrinsically increase more recurrent circuit, and what I think my question is, so of course this is a task, so you can also do it by the feed-forward network, and so but what's so we can do it for by the feed-forward network and also do it by a recurrent network, and the recurrent one because it has higher phi, and then probably you think it has stronger autonomous or agency. But what's the physical difference between the two systems?
Yeah, that's a very important point, and I'm glad you asked actually, because I didn't have the time to go into that during the talk. So there's this Krohn-Rhodes theorem, I think, that basically says that any recurrent network can be implemented by a feed-forward network. But the feed-forward network doesn't have the same number of nodes. It might have many, or it might need many more elements to implement the same function. And actually, the more memory is necessary to perform the function, the larger the feed-forward network is usually going to be able to capture the function of the recurrent network. So if you have any kind of energy constraint or other limitation on the number of elements that your agent can have, then integrated systems will be preferred, will have an advantage compared to feed-forward systems. And in the experiments we did actually not put an explicit penalty for more nodes, but there was a hard upper bound on how many hidden units you could have. And so at some point for the more difficult tasks, it's harder to find a good solution of a feed-forward network that could still do it with so few nodes.
I think my following question is this proof that the computational cost or energy cost is really less for the recurrent one than the feed-forward one?
Yeah, not for every task, but for many tasks, yes.
I mean, is it proved?
Oh, is it proved that it, so I mean, so what I can say is that the opposite is not proven. So I don't think it's possible to I think it's quite easy to have an example where you have a recurrent function that just cannot be implemented by a feed-forward network with the same number of elements. And once you need more elements, you do need more energy if you compute them as like bits or.
Yeah, so I totally agree. You need more elements, but for the recurrent one, you also need more time, right? Because the feedback to your previous node, you may need more computational time, and
No, not necessarily, because like the point is the layers, right? So I could have a feed-forward feedback network that has, let's say, 3 nodes, but they cycle through a loop and then give some output that depends on basically my last 3 states of the system. And the feed-forward network would have to be, let's say, in a particular case, it could have to be like 8 nodes. So in order to still get those 3 time steps of memory, you also do need 3 layers in the feed-forward network that one node feeds forward into the next node, feeds forward into the next node, right? So the time steps are actually the same. It's just a matter of, and they might even up. So the feed-forward network might actually have to do everything faster than the feedback network.
Oh, thank you. I think I will ask you the question privately.
Okay. I think we should go to lunch because we already have an hour over. But let's thank Larissa again.